I'm going to talk about the role of edge computing in age of machine learning and energy constraints, and give you some sort of feel for some of the research that we are currently conducting in this space. Many others are conducting as well. But I think this is a very important topic that is currently coming up. Since we are also seeing the limits of cloud computing, this is actually some of the graphs from 2009 when it was basically discovered by and argued by Satya from CMU and others that the cloud computing cannot support, if it is currently remotely used by interactive applications, cannot support sort of real-time spaces. So for example, frames per second will be 10 frames per second if you are starting to send sort of remotely data. And so you are starting to see sort of 100 milliseconds, 66 millisecond sort of really sort of long delays, for example, for AR, for VR, interactive visualization applications. And of course, if you have something very local on your computer, the delays are so much shorter. And also this particular argument actually from 2009 is making the comment that you are having these tremendous Internet 2 type of round-trip delay times that are really not very conducive to many of these interactive applications that we really want and our future. And so I think I want to just sort of give you the feel for a more historical space that in 2009 this group of researchers made very, I think, clear case for edge computing, where you basically will have some of these devices at that time, you know, some of the smart glasses, maybe some mobile phones that basically get connected to your local area through your local area network, basically to a server to actually get offload some computing and get sort of this real-time interactive latency. And Satya actually gave a talk at that time at Illinois, and he talked about the Starbucks application where basically you will offload maybe a virtual machine and get sort of a computation if your particular mobile device doesn't have enough resources, and you can really in real time interact. And so basically the argument was that there will be a soft state, it will be management will be self-managed, it will basically be a data center in the box, right? The latency will be LAN in comparison to the far reached sort of cloud. So I think forwarding to 2024, if you start to look at all kinds of sort of websites and business predictions, we truly have now basically a tremendous growth of edge AI. A lot of AI applications are happening. Another sort of really great thing that is happening is that the networking, the 5G, 6G is coming, and it's connecting actually many of these IoT devices or these mobile devices with these edge devices, and there is really a networking edge computing synergy. Of course, now that basically these edge devices are getting also much more powerful, you start to deploy containers, and you can start to have also scalability, deployment, and easy application lifecycle management. But also I think what triggered this growth, I think, in the edge is that it is providing a technology of for enhanced security and privacy, and particularly with algorithms like federated learning, homomorphic encryption, that can basically enable this kind of edge cloud sort of type of connections. You can have a private edges that are processing the data, and then cloud can basically just do some more assisting role and assist in data analysis without sharing the particular data. And many other trends, actually, I found it very interesting that this edge computing is now enabling Internet of Things and edge as a service and so on. So, of course, another trend, big time, is with respect to the machine learning that we are seeing tremendous amount of devices across cities, surveillance of video analysis, and we basically can process these particular analysis maybe closer to these particular sensors. Array of Things comes to my mind in Chicago, right, where there is a lot of these various traffic corners are being equipped with Array of Things boxes to actually process the data on edge devices and then report the data maybe to University of Chicago. But you have the question and answer services doing machine learning and healthcare, of course, it's model training, big sort of AI spaces that we are currently seeing. And so I think we are seeing this convergence of edge computing, these IoT devices, and large scale systems, machine learning systems, and particularly because this edge computing does enable, with particularly these real-time networks, 5G, 6G, Wi-Fi 7, real-time analytics for various machine learning applications that really require low latency. And this is currently what is really coming to bear from the vision of the 2009 of the edge cloudlets to actually start to see this. Another thing is that edge optimized AI frameworks and tools enable intelligent applications that are closer to your smart home. And of course, as I want to argue through my talk, is the privacy sensitive approaches such as federated learning now enable running AI on these private edge devices, and you can collaboratively basically train machine learning over decentralized data sets using federated learning, and then keep also these individual data private on the edge devices. So that was sort of some of the arguments that this edge and machine learning are really coming together. But we actually are sort of studying as being part of the multimodal and being part of the Internet of Things, edge computing, and now machine learning. We started to sort of look at some of the challenges, and there are truly multifaceted challenges with these systems. And particularly big challenges happen in training, right? How do you do distributed training across this particular edge cloud type of systems? And so the federated learning systems, a lot of research is now spent on training where the edges would be private and they would be connected to some of the IoT devices, or they themselves basically have sensors that are currently creating a lot of data. And so these private edges do start to see computational intensity. They are consuming energy, and many of them applications basically do need to respond in latency sensitive manner. So basically that particular requirement on these private edges will require that we do start to look at multifaceted resource challenges, because you do need to look at latency, you need to look at energy on these particular edge devices as they are serving federated learning systems. And that really means then to look at the almost synergy of computation and throughput, energy consumption and execution latency as you are training your federated learning systems. So I want to sort of talk about some of the approaches that you are seeing in the literature in terms of optimization opportunities for these machine learning training systems. And one of them is you can start to reduce the amount of data. There are systems like Redactor, for example, do frame filtering from the cameras if they are sort of similar. You do video compression, right? Sort of bit resolution might be very much attention-driven and so on. And these particular approaches, like the data redundancy, will help you in optimization of bandwidth, optimization of throughput, as you are currently moving the data from these IoT sensors to the particular edge devices. Now, you also can start to play with the hardware configurability, and we currently have these various edge devices that are having CPUs, they have GPUs, right, Jetson Nanos and so on, and also RAM. And these particular particular hardware components actually in edge devices do have now very different configurations in terms of voltages, frequencies. There's a tremendous heterogeneity of these edge devices that you can now start to basically think about optimizing towards energy and towards latency. And then the third potential direction of the optimization for these machine learning systems is actually to start to address the machine learning models themselves, particularly the sparsity. You can do quantization of the parameters, model pruning, right? Not so many neurons, gradient compression, and many, many other techniques that are currently being researched in the community. And that actually then can help you with latency, with bandwidth resources, and also energy resource. So we basically looked at this particular space, and we felt that in these are general machine learning approaches that people are sort of studying. How can we bring them into the federated learning training optimization? And so I do want to go just with one slide for the federated learning, what we are currently considering as to optimize this kind of federated learning over the particular edges and do collaborative, basically, training. In the federated learning workflow, we do assume that the server and then the edge basically are in communication, and the device checks basically with the server, and then the server basically does certain selections of these edge devices from which basically it wants to get data. So this particular server will actually, during the configuration phase, try to select the particular clients, and if the clients are being selected, they have the right data, or they are sort of have the right maybe resources and so on, then basically this particular, it will get selected, and the server uploads model and training parameters to that particular edge device. And then with this particular model and the private data, there starts a training. And this particular training, we are going to be assuming that there is a certain deadline by when basically you want to finish this particular training. So on device, on this particular edge device, you start to do the training. The model gradients are then reported to that particular server cloud, and then the server basically aggregates it, updates that particular global model, and then training moves basically to the next round. So this is particularly the round that we are currently looking, and the training might go through several rounds in order to sort of find the right model on each particular device to actually provide the right parameters so that then inference can start, right? But this is about a training aspect. So for this particular federated learning workflow, what we are going to now sort of see is how do we run these various machine learning models, but also in an energy efficient type of manner. So we are going to talk about one of the systems that we have been researching together with IBM. This particular work is actually funded by an IBM research center, and IBM currently having major efforts in hybrid cloud, looking at edges and cloud computing, and energy is becoming really important for them. So we have been exploring some of these energy aspects on the particular edge. So one of the really big issues is that as you are running very diverse type of edges, the training can last in every round different time, right? So because the particular edges are heterogeneous, and so they are running maybe the training much longer on a mobile device versus on a laptop or your iPad. And, but the goal for us will be that we actually finish the execution on every of these edge devices by a particular deadline. So some of the devices might be much faster, like the particular laptop, and then they are basically just done. And the reason why they are so fast is because they run at very, very high configuration frequency and are very fastly done, where the mobile device basically is slower, has maybe lower frequency or lower voltage sort of resources, and therefore the training lasts longer. And so we do want to apply dynamic voltage frequency scaling, which is a quite well-known algorithm in modulating the frequency of your CPU, GPU, memory. And we want to sort of apply to actually slow down the training phase for these fast devices like the laptops, so that basically they don't use as much voltage, as much energy. And that basically we would like to sort of apply and understand how to then bring it together in this kind of training machine learning spaces. So one sort of interesting aspect is that these frequencies you can now modulate, and that's really the fun part. On these edge devices, you can modulate frequency of CPUs, you can modulate CPU frequencies, and also memory, basically. And the slower your hardware components run, the less energy they are using. So energy consumption is then reduced, but you basically are still satisfying the particular deadline. Now, the challenge in this particular configuration space is that now basically many of these devices come with many different configuration levels. So for example, in the GPU level, you have several sort of multiple frequency and voltage scale levels. CPU, basically, you can go from 0.8 megahertz to very slow to basically 1.2 gigahertz sort of type of frequency. So actually you can, between these three resources, GPU, CPU, memory, basically you can go up to 2,000 combinations, right? And dynamic voltage scaling sort of type of combinations. And so that is complex, right? Which is currently the best configuration that you would like to sort of find in order to run then your training with this kind of configuration and save energy and still meet the particular deadline. And so really the ultimate goal is what is the training speed, right? In this particular x-axis, so the faster you go, but the less energy efficiency you have. When you go with high energy efficiency, you might have a lower training speed. And of course, the goal for us is going to be to find the Pareto front, right? The best sort of configurations that are having the right training speed and also the energy efficiency. And the challenge currently is that to find these particular sort of optimal configurations, there is non-linearities, there is neural network model dependency, hardware dependency, quite a sort of a complex system, as we know from many of these optimizations that I'm sure you are looking at. And very often this particular finding the right combination, best training pace, it's basically a black box, right? You you could sort of find functions and so on, but it's just very, very complex. And so you try to treat this particular mapping from all of these 2,000 configurations to the right Pareto like a black box. And so that basically currently for us in this particular work, we wanted to find the methodology, how to find the best configuration in each round. Remember, basically in the training, the server basically gives you the model, you have the data, you need to now online basically process, find the best configuration, and then run this particular training and then return the gradient to the server, and then the next round comes. So that's currently really what I would like to sort of talk about. So the big challenge is how to select the best DVFS configurations for each round of the local model training. right? And you might have, the challenges are different execution deadlines for each of these particular execution rounds, right? So the mobile phone and the iPad might have very different execution deadline for each round as, for example, the other type of machines. So how to select this particular sort of best configuration, you also need to do it online. There is no access to the neural network model before the particular federated learning task is running, is giving to you for performance profiling. So you truly need to have some kind of configuration finding algorithms in real time and right on that particular device. So finding the Pareto DVFS configurations as a black box optimization in online form, that is currently our goal. And many of these systems that we are building, I think, have to have this kind of capabilities. So I hope that some of the discussions will be helpful to you. So we currently have been dividing the whole search for the best DVFS configuration into 3 phases. In the first phase, basically, you do so-called safe random exploration, where you take sort of random samples of these particular configurations of the GPU frequency, of the GPU, CPU, and memory. And then you hope to basically get certain understanding of the points that will sort of come hopefully closer to the particular Pareto front. And then basically some of those samples that you collected, you are then starting to use for Pareto front constructions, and I will talk more details about that in the phase 2. And then actually at the end of the Pareto front construction, you hopefully get a set of points or a point that you can then use as a configuration in the exploitation, because then basically you can start running the training of your model over that particular data on each particular device. So let's look at sort of the individual phases. So in the first phase, as I mentioned, you are actually running, you have a certain set of these configurations, think about 2,000 configurations of GPU, CPU, memory sort of capabilities, frequencies, and you pick as many as possible configurations, and you measure exactly actually what is currently the energy under which when this particular configuration is running, and what is the latency, right? How long particular training would be running, and that particular under that particular configuration X1, you are running batches of mini batches of the training data. And then you have another configurations, and you are currently again measuring latency and energy, because that currently what we would like to optimize, right? We would optimize minimize the energy usage and minimize the latency. And then actually at the end of this particular exploration, we also want to run the whole sort of model with the mini batch data at the maximum configuration. Remember, when I put 1.2 gigahertz of CPU and I put the maximum frequency of GPU and so on, there is definitely we will meet the particular deadline, but it takes a lot of energy, but it's very, very fast. So you want to also have that particular powerful configuration measurement in your set. And so then basically you have now within that particular time that you allot to the particular exploration, right? These random sort of sampling goes X1, X2, X3 and so on configurations. You take basically the best couple of sort of sets, and you are now starting to go into the phase 2 when you want to start building the particular Pareto constructions with Bayesian optimization. And again, again, quite well-known framework. Bayesian optimization is a sample-efficient methodology for optimizing expensive to evaluate black box functions. And in some way, you are getting a sort of maybe few points that you currently get from the observation, from the previous exploration. And now during the Pareto construction, we currently still have a lot of sort of regions which have a lot of uncertainty. And so we will be running certain sort of, again, samples that will new observations that we will hope that are getting us to much more precise Pareto front, approximation to the Pareto front. The uncertainty region will be smaller and smaller. And with any of the new points, we will also calculate the posterior uncertainty, the posterior mean, and that goes again to the multi-objective Bayesian optimization. Remember, we are having multiple objectives because we want to optimize energy and latency. And basically, after this particular Pareto construction, we hope that we are going to get a couple of these particular points, right? Sort of as these new points get sort of run, and hopefully then this particular region gets smaller and smaller. Then basically we are having at least some sort of good set of points here that we can use for the phase 3. And in the phase 3, actually, what we do want to, so in this particular Pareto constructions, I wanted just to comment is that you run this particular Pareto construction with the Bayesian, so you run training round 1, right, with a particular set of configurations. Then you are calculating posterior distribution. You augment the Bayesian optimization, and then you take another sort of configurations, and hopefully you are sort of shrinking the uncertainty region, getting more and so closer to the Pareto distribution. So you generate a batch of K configuration that you explore, then try these particular K suggestions. You measure again your latency or energy, throw some of those out that are not close to what you are looking for, and then basically you're updating the posterior estimation, generate another K configuration suggestions, and so on. So you basically are hopefully getting sort of close to this particular Pareto distribution, but you still have a couple of these configurations. And so at the beginning of the exploitation phase, where we want to actually use sort of the winning configuration, what we will actually do is we will run an integer linear programming sort of solution optimization, because now basically among these particular points you want to select a configuration that minimizes the energy consumption, does supply to that particular constraint of the deadline that is not missed, and that now basically under this particular sort of smaller set of the linear programming integer is basically clear to sort of solve. So the system architecture, the software architecture is basically very sort of straightforward. We have basically the federated learning task executor that brings basically these models, and also takes basically these the control configurations and runs basically a particular model on each edge device with the particular measurement through the observation of the latency and of the energy that they are using, and that basically then gets stored. And that particular, again, through the exploration and through the Pareto construction and then the exploitation, we currently basically are using the optimization solver, right, to find the optimal configurations for the DPS controller. The whole set of frequencies get settled and given basically to the task executed. The Pareto construction basically is being calculated through the MBO, multi-objective Bayesian optimization, at the beginning of each training round. So that's basically why it is currently running. So normally, basically, the path goes through this way, but this particular is running sort of at the beginning of each of those training phases. So we have been curious then how does this particular approach work, and does it how long does it take in order to run this particular optimization. Usually you would anticipate that the explorations where we basically take the random, even the Pareto construction should not take too long, and then the exploitation time is the most longest period that you currently run under sort of a winning configuration. So we have been experimenting with the JSON AX and JSON TX2, probably you know all these particular hardware of, they are sort of having nice, as I mentioned, they run with from 0.42 gigahertz to 2.2, and then the GPU basically goes up to 1.3 gigahertz. Memory sort of frequencies can be nicely modulated. We have been looking at different neural network models that get uploaded from the server to the edges. Several of those have been vision transformers, ResNet 50, and also LSTM. And the data that we have assumed on different edge devices has been the CFAR and ImageNet. These are well-known sort of data sets, text data sets, or image data sets. So here are some of the sort of results that we have been actually quite happy with. On the x-axis, we have currently the rounds, right? This is currently the round that includes the phase 1 in terms of exploration, then the Pareto sort of construction, plus the phase 3 where you are exploiting this particular winning constructions. And you can see actually that the exploitation does take much, much longer. That's basically where you are hoping to save a lot of energy and run basically all of your neural network models training by the deadline. And this is currently the exploration, where currently you might use a lot of energy, but you still sort of, it's a short time. And then basically this is currently some of the Pareto constructions that you are exploring a smaller subset from the exploration, and again sort of are trying to sort of get smaller, even smaller and smaller sets through the Bayesian optimization. We basically tested it performance. This is currently an algorithms when you run through every round the maximum GPU, maximum CPU, maximum memory frequency. So you can see currently that the energy consumption is very high if you basically run and you are not trying to modulate some of these frequencies. This is currently, sort of different type of sort of deadlines when you are currently have 4 times sort of this time minimum, so currently the delay we have been modulating, for example, the rounds would be by 150 seconds, right? And sort of that, what are they? And if you are starting to decrease the deadline, right, then we can again having maybe deadline of 75 seconds, right, and so on. So 2 times DLL min, and again we can basically get pretty good estimation of a good configuration for the exploitation. We have also, this is currently, this particular orange is an oracle. If I know exactly what this particular neural network training tasks should be looking like, so profiling, and then basically I know exactly what particular configuration they should be taking. And so we have been quite happy that during the exploitation we can match pretty well the oracle space. And we were also curious, basically, how does the multi-objective Bayesian optimization perform as a systems overhead. As a systems person, I do like to know these kind of things. And so again, you can see on these particular two edge devices that you are currently sort of seeing maybe 8 seconds, some of the optimizations. Here on the AX, it was 7 sort of seconds, and they are again consuming also certain amount of energy. So you do need to consider that particular sort of overhead, or energy overhead sort of general by this particular MBOS you are currently training over the different types of data sets. So that was more sort of on the computation and really taking in these edge devices in the federated learning, the aspects of resources that currently need to be there for training. And I wanted sort of to share some of those sort of considerations. So there is a lot of very interesting problems, by the way, in the federated learning. But one of the interesting problems currently is that you are between the edge devices and the cloud sharing different, you are sharing these particular gradients or change in the gradients. Different federated learning have different approaches. But one of the important aspects is that you are also having this heterogeneity of these devices that could actually serve as edge devices. And as you are training them through the rounds, and in each round sort of you have the epochs, some of these particular devices might maybe have more data or less data, and can be slower or faster. And that actually creates the problem of stragglers, right? That particularly if you put some of the deadlines by when basically particular round should be reporting your gradient, your learning to the server, you might not finish, right? Because your particular device is just too slow. And so that's currently quite well-known problem. There are some sort of approaches that basically by the deadline you cut off, and whatever partial result you have, you report the partial result. Meta currently is millions clients of federated learning. The Papaya sort of has demonstrated that they are having per client training time distribution spans over 2 orders of magnitude. Yeah.
Yeah. Can you actually, like in this case, I'm wondering if you can execute 2 times the tablet, because the tablet and the computer use less time, right? You can actually maybe
right,
like you can actually like that.
Right, you could, right? I mean, the issue currently is that maybe there is a certain expectation of very similar data, right, that you are currently. So I can give you one of the very interesting examples is you are currently looking at cameras that are currently taking a crowd picture, and you are looking for a child. Right? You want within that particular time frame to process on your edge devices and look for that particular child. If you start to sort of go ahead, right, that sort of misses your time, right? Because the slow device basically looks at old data, and you are already looking some of the sort of data, or basically maybe there is no data, right? If you are currently looking at real time that these IoT devices are providing, right? So there is, yeah.
So although in theory the computational task is very complex to find this source of mediation point, in practice you mentioned have many degenerate solutions where it might be the trivial case of finding the most efficient and most capable device and running that 100% and then going to another one.
You have, and there are sort of, I mentioned at the beginning that, you can do device selection, right? And there are some very interesting solutions, for example, that you can bid, right? And whoever has the highest resources bids highest, and it gets basically, yes, definitely. As I mentioned, this particular space is tremendously rich. And we currently are sort of talking about data sets that are already there. But think about some of the federated learning and in real time. I'm currently having a camera, and the particular camera is collecting, or as I said, in the crowd. And so there, basically, you have a time, right, synchrony, right? And you want to finish some of the training and then sort of finding the best, sort of data. So you might not sort of have sort of these particular, the straggler is still a problem, right? But you might maybe not select this kind of slow device, right? But we were sort of curious, basically, if you would have this kind of slower device, how would you actually organize the data that within that particular time frame that each of the edge devices would process, that how do I select the right data, right? Rather than just cut off and sort of do things. So we currently have been sort of looking at this particular problem, mismatch between sort of the client computation power, the training sizes, data, and some of them sort of don't have the good hardware or the data sizes there. We have been then reaching to, there is a mathematical construct, coreset. Many of you might be familiar with that. And that is currently basically, I think, a better way to go about finding the right data, as we are currently sort of selecting the right data to do the machine learning processing over. And basically, coreset is a subset as of the whole training data set, where the machine learning trained over S will give you basically very similar performance as the model would be trained over the overall data, right? And now in our particular case, we were also curious how to do this kind of distributed coreset training, right? Basically in data sort of selection. So the challenge in this particular case is how to select the data samples that best represents the whole data set. And we basically wanted to cluster the data, the training data, and then find basically gradients and sort of look at per sample sort of gradient similarities, and then form a coreset using this particular cluster centroids. And they basically would be then the representatives over which we would do the training, how to select data samples that best represent the coreset. It's a weighted selection and collection of the cluster centers, and so you can basically start to maybe put them together. And then the federated gradient update will be a weighted sum of these coreset gradients, right? And you basically are then sending them to the particular sort of server. And so you are having now in each of these particular edge computers different coreset for each round, while basically the model is being updated. They have to be updated since the data is basically changing. So generate basically per sample gradients over full full set periodically first from time to time, so that you have a certain ground truth, right, as you are also selecting sort of some of the coresets, and then update the coresets with respect to the updated gradients, and you are looking at the shortest distance between them. The full set and then the coreset. So in some way, with this particular system, we wanted first to have a period where we are looking at the full set and analyzing the sort of the clustering and then calculate per sample sort of gradient, and that actually can allow us then to generate the coreset generation from the set V. And then basically in the next epochs of that particular round, we can then use only these particular centroids of these particular clusters, and then as data that are being now trained with the neural networks. And there is basically quite well-known optimization, again, framework of the k-medoid clustering in this gradient space. You are looking at the shortest gradient distance between the full set gradient training and the particular coreset gradient training. There is, of course, certain threshold how big you want actually your coreset to be as a constraint. And so we basically, you can then select, and hopefully you basically are decreasing the amount of samples, right? In that weaker device, you might have 50 samples, and in the larger, you might have 300 samples to actually create the data and use them. And of course, then you are also saving some energy on these particular sort of weaker devices. And so we actually were also very interested in, can we sort of optimize this, there are again algorithms, FastPAM, to basically get these particular centers of these clusters. And also you can then start to limit actually your loss function between the current system and then sort of your optimal ground truth. So again, we were very curious about does this particular system provide us with solution for these stragglers? Are we currently having a good training capabilities? So we have been again looking at different data sets from these particular data sets with the numbers to sort of Shakespeare's text to some of the sort of synthetic data, looking at different samples and clients, a number of sort of clients, and we have been pretty sort of happy in terms of the particular sort of results. The distribution of these training samples was in terms of number of samples that we wanted sort of to decrease, right, in terms of weaker devices. And we also wanted on the client, on the server side, run different aggregation techniques and compare them with our type of technique, so the federated averaging or FedDS, which is a deadline-sensitive version of Fed average. And also FedProx is actually handles partial training, right? It basically cuts off wherever currently you are finishing your deadline. So we were very curious if this particular works. So in terms of the results, we have been looking at number of rounds on the x-axis, and then basically if we have 10% of the stragglers, what is currently the training loss? And we you can see basically that the more of these rounds you are running, the more we can actually create better and better type of coresets, and overall then basically the loss gets smaller and smaller with respect to our FET core, where currently when you do just a FET prox, for example, you don't set up coresets, but you are just cutting off wherever currently the training deadline had to finish in that particular round, that you might then lose actually some of the there is a higher training loss. Currently I feel that in this particular MNIST, there was more sort of difference between these different approaches in terms of the global optimization. You can see actually here currently, for example, on this federated average, some of the differences are also much larger. But overall, basically, we have been performing pretty well. If you have 30% of stragglers, one of the reasons actually you mentioned in terms of selections of these devices is you can select sort of always the best one. But there is currently also in the community a concern about bias, right? That basically you sort of remove some of those particular edge devices and devices that might have some interesting data, but don't have as much sort of computation and network sort of power. So we did wanted to understand if you have 30% stragglers. And again, we thought that for this particular approach of the MNIST be performed well in this for this particular coreset setup. Also, in terms of accuracy, right? That's another sort of important aspect of detection and sort of the test accuracy and training time in this particular case. So we currently have achieved, actually, with our training of these coresets, again, in the MNIST, 10% stragglers, 30% good performance in terms of then analysis and accuracy, top accuracy, object detection. And also the mean training per round, you can see currently that the Fed average approach has taken very long time, where we are currently in the ballpark of the performance in terms of training with these particular coresets. So yeah, so we basically have been, as I said, happy with that particular result. So in conclusion, I wanted just to very briefly talk about the edge computing. I think is currently really being utilized for offloading, and you probably see many other applications now, basically even in wearable computing, right? You have energy being created on sort of the wearables and being or powered basically by edge devices, but we are seeing just tremendous amount of growth of these edge computers, edge servers. One of the sort of applications we have been also looking at is neural network compression from cameras. Currently, the cameras are currently getting very powerful, and so you can start to basically train offline the particular imaging and attention areas, and then basically decide based on that particular attention areas where you currently want to invest more bits or less bits, where you want to quantize more bits or less bits, and so this context-aware image compression, again, with for these particular edge devices, especially if you have a lower bandwidth network. And then actually when you are putting more bits into the attention area where you want to do image classification, will for video analytics in the edge devices can be also very helpful. So neural networks currently you are seeing in compression, you are seeing it on the edge devices for the image classification, for object detection, that will, I think, are sort of tremendously helpful. There are many demonstrations currently with the UAVs that are currently processing, compressing, and then sending data maybe to the ground for to the edge computing as well. So I do want to sort of conclude that the rise of edge AI is becoming, I think, very real. We have maturation of these neural networks, tremendous advances in computer infrastructure, as well as adoption of the IoT devices. Benefits, I think, we are seeing of the edge AI getting basically reduced cost, increased privacy, as we talked about through the federated learning, high availability, I think, of these edge devices. And you can see currently a lot of these companies, Amazon, basically Greengrass, edge computing, right? The Cube Edge currently is from Kubernetes is coming to the edge computing. So I find that there is just a lot of very interesting systems, but also AI type of sort of problems. And I see currently still a lot of challenges in this edge AI for optimization of the resources to achieve this kind of sort of low latency, particularly if you start to actually think about wearable in healthcare, for example. How do you currently work with the edge devices that are on your body? Can they be sort of powered differently? Model deployment, I find that that's currently again, as we are starting to see larger and larger models. So one of the very interesting aspects for me is looking at LLMs and the large language models or visual language models, right? Can we currently, for example, configure from large language models, smaller large language models or visual language, and then store them on these particular edge devices so that basically you can have a IoT device, basically interact with the small LLM and get basically answers, for example. So I think we are going to probably see a lot of sort of work in that particular area, right? That sort of scaling down these particular language models, large language models, visual language models, domain-specific models, and then put them on these particular edge devices. So that actually might mean that we will also need, now basically large language models are being trained on large data centers, but we will need then sort of have some kind of training capabilities of these small language models and then continuous learning on these edge devices, right? Sort of as they are collaboratively working together. So I feel, training models and their deployment as well as integration of these various different sort of heterogeneous platforms will be very, very important that I think we will see a lot of solutions actually in this community. So yeah, thank you so much for listening and open to questions.
Okay, we have time for a few questions. Okay, let's start with Klara.
So a classical consideration in distributed system is what is the impact of local failure on global behavior. But I didn't see here, you mentioned what happened when you have failure of edge nodes.
Right. So there currently, we have not looked at that, but I could actually see that the server would have certain percentage of responses, right, of the gradients to decide. And in some way, when you do have a failure, right, and none of the sort of gradients are coming, then the upgrade that's happening every round, right, might happen on a smaller number of responses, right? I mean, and so maybe you are coming back to that particular edge device in the next round, right? What is happening? Here is currently an update. And to some degree, you could actually consider the round almost like a selection, right? That particular device was selected, but did not respond, right?
That's a benign failure. They just don't send a message.
Yeah.
But what if these nodes are being corrupted?
Yeah. So absolutely.
They send your own data.
There is actually currently very interesting set of research results as well that currently you are starting to think about that these edge devices become malicious. And then actually the question is, can we at the cloud have different weights of different contributions of these particular services, right? That you might sort of minimize. But this particular this is a real threat, actually, that that a malicious edge device starts to actually color all your data, and then suddenly it goes towards a very, very bad sort of gradient, and you are updating all benign devices. Yeah, we have not looked at it, but there is actually CCS had some really interesting papers. So I know that the security community is looking at federated learning and this particular attack. So it's a real threat. Yeah, that's very, very true. Yeah.
Okay. Other questions?
Interesting talk. You use the NVIDIA Tegra boards. Those are usually powered by the wall. And have you looked also at, let's say, battery-powered devices in the sense that your parameters of dynamic voltage, frequency scaling could also be affected by battery state as another parameter? And then at the end of your talk, you talked about communication. So that's another parameter.
Yeah.
Compute versus.
Absolutely.
Okay. So can your framework be extended to include more parameters without exploding the search space?
Right. So we have not looked at this basically a variable energy supply, right? And we are currently actually within the IBM Center, they are interested to actually power their servers with renewable energies, right? And there basically we are starting to look at load balancing, right? Basically what happens if you have a certain supply of energy, how far can we go down in terms of the dynamic voltage scaling, and when do we start to actually offload something, right, out of the edge devices because there is not going to be enough supply. But I have not looked at in this particular work, but that actually really will require that we have very good monitoring capabilities of these batteries or of these renewable energies. And in that particular center, we are starting to look at that. Particularly, for example, it's the whole distributed computing and migration of workloads, right? That, when is the particular threshold when you start to migrate, particularly if you have AI workload, ResNet, right? You have, where are you currently finishing to actually move something else, right? Not clear, right? So I suspect there will be some of these configurations of these machine learning models. Then do I move data? Right, into other type of servers. So there are currently some of the ideas that you have a very hybrid model in that particular cluster, where some of them are on the grid, but some of them are on the renewable, right? And can they basically on the grid be sort of the last backup, right? But we have not sort of looked at this particular problem. But it's a very important problem, and the IBM people actually are looking at interesting aspect of having different data centers. So it's not about edge computing, but much more cloud computing. They have different data centers across the world. And so when are they starting to offload everything, right, to Australia, because they have a lot of sun, right, and so on. And so this load balancing, migration of data and AI workload, and what are the good points to break them, it's a question.
We'll take one more question.
Yes.
Okay.
So there is in learning fundamentally the diminishing returns that happens when, after the first couple of epochs, for example, each epoch typically gives you worse, slightly better performance, but there is diminishing returns. So when you are conducting this training, do you also keep track of your performance for example, 90% performance, 95% performance on these data sets? Do you potentially run test data sets on some devices while training with others so that you can monitor how well you're doing with the task?
So we have been, you are currently looking at the particular task if I go under maximum configurations versus when I am going currently low. Yes, we have been looking at, and so far we have actually, the training quality has been very good in terms of then providing this particular result of the training to the inference engine and accuracy. So yes, yeah.
At this point, I would like to thank Klara again. Thank you very much.